Okay, my lab is frictions and springs and such. So the purpose of this lab was to try and find the coefficient of friction between like a metal like hanger mass and the top of this, using only this and some masses. Well, knowing only like the mass of this and the mass of some masses that I put on it. And yeah, so my equipment was a dynamics cart, two 200-gram masses, one 10-gram mass, a Post-it note, and a ruler. So here's my equations that I had to use. So the force of spring is equal to the spring constant times like how much it's compressed. Force is equal to mass times acceleration. The force of friction is equal to mu times the normal force. And then this is just like specifically for this one, but the normal force is equal to mass times gravity, because if you draw out a free body diagram, it would be stationary in the up and down direction, meaning that the net force on it is zero, and the only two forces acting on it are the normal force and gravity. So that would mean that the normal force would just be equal to the force of gravity in the opposite direction, so m times g. Okay, so the procedure went kind of like this. So I took this dynamics cart and I held the spring out, and I took one 200-gram mass and I placed it on top and saw how much it compressed. And then I took a Post-it note and I put it on there so that its bottom was just like barely touching this part. And then I removed the mass and then saw how far away the end of the Post-it note was from this, and I measured that with the ruler, and then I recorded that down. And then I did the same thing but with a 400-gram mass, and recorded how far they moved and such. And that was part one. And then part two was I placed the 10-gram mass on top of this, on like a place I could recognize if it moved or not. So like I kind of just ended up placing it with its back touching this wall right here, this back wall. And then I would push it into the wall and place the Post-it note on the edge, kind of like how I'd done, and I'd release it. And I'd see if it moved or not. And if it did move, then I would move the Post-it note slightly in, and then push it to that point and release it. And I basically did that until the mass didn't move. And I figured out just about how far I could push it in without it like moving from where it was. And yeah, then I measured that. Okay, so for my data, I got for part one, the 200-gram mass moves the spring by half a centimeter or 0.005 meters, and the 400-gram mass moves it by 0.015 meters, which I thought was kind of weird. And then part two is at when I push it in a total of like that much of 2 millimeters is the like only time that it really doesn't slip. And then I measured the mass of the cart, and the mass that I had on top weighed 10 grams. Okay, so now for the part one mathematical analysis. I wanted to find the spring constant of this spring. So what I did was I thought, so the force of the spring divided by the distance it's pushed in is equal to K. But then I thought so what I did was I had the force applied by the 400-gram mass minus the force applied by the 200 grams is equal to, well, so I did the change in force divided by the change of the amount it moved was equal to the spring constant, because like it's moving 1 centimeter, so that would mean that the x would be 1 centimeter, such, yeah. So that's what I did here, the force of the 400-gram mass minus the force of the 200-gram mass divided by the distance it moved, which would be 1 centimeter, is K. and that was 196.2 newtons per meter. And then, so I kind of plugged that in back in to check it. So I got the force of the 400 gram mass times 9.81 divided by the spring constant would be equal to the distance it compressed. But it wasn't equal to the distance it was compressed. It was equal to the distance it was compressed plus half a centimeter. So based off that, I concluded that the spring inside here, when it's all the way extended, is already compressed. Okay, so I kind of thought, you know, like it says it should be compressed by 0.02 meters, but it's not. So I figured that basically the force of the spring, since it's already compressed by half a centimeter, so the force of the spring, just for this specific spring, would be 196.2, which is spring constant, times 0.005, which is the distance it's already compressed, plus the additional distance compressed by that. Okay, so I figured that the mass on this cart will move compared to the cart when its acceleration is less than the acceleration of the cart. So I figured out the acceleration of both of those things. So basically the since force equals mass times acceleration, this part was the acceleration of the cart, which would be the spring force, which I know how to calculate, plus the mass of the cart, plus the added mass, which is 10 grams. And then this over here would be the equation for the force of gravity. Oh, not the force of gravity. The force of friction divided by the mass to get the acceleration again. And so that's simplified here to just the masses are removed. And then I divided both sides by g to get the force of the spring divided by the mass of the cart plus the added mass times g is equal to mu. So I plugged that whole thing in, and I got a spring constant of, not spring constant, coefficient of friction of 0.0274. And this slide's just for final thoughts. Yeah, this was pretty cool. I originally wanted to figure out the coefficient of kinetic friction, but that didn't really work out because I'm pretty sure that has to do with like jerk and stuff. I don't really know how to do that, and I was trying to figure it out, but I didn't. But yeah, this is kind of cool. Yeah, that's it.
Questions?
Questions?
So in the future, I suppose you would want to find kinetic, but if you were to do this again, what would you do differently?
Oh, well, I'd probably figure it out with different carts, because like a different kind of dynamics cart, I guess, because this one only compressed like 2 millimeters before it started slipping. So I kind of wanted to do it with a weaker spring, so that I could compress it more or less and get more specific, so that like the distance I compress it, like I compress it a longer distance and it changes the force by a smaller amount. Yeah. Okay.
Yeah.